So as you'll know, if you were watching a previous video, I made an 8-bit EEPROM. I actually called it a MAN-PROM, a manually programmable read-only memory, which was just one of these green boards here. So what it is 8 bytes of ROM. Each one of these stripes across here is a byte of 8 bits, and you can set the value in the EEPROM at each of the locations by flicking the little tiny dip switches, which is easiest done with a very, very tiny screwdriver. They're a bit too fiddly to do by hand. So if you put one of these switches, well, what could we do? If we put one of these switches down, it's an off in that position. One of these switches up, it's an on. So 8 switches together forms 1 byte, and 8 bytes, there's 8 bytes in one of these boards. It's a bit of a crazy thing to do, but I thought it'd be quite interesting. So then I linked 2 of them together, so I've got a 16-byte ROM, and I've then linked all of this up to a counter, which is down here. That says 74HC163, so it's a 4-bit counter, so you know that it can count from 0 to 15, and the address lines from that counter are going to the MAN-PROM, and I can clock it from here. So when I send a clock pulse in, this is working as effectively as a program counter. It's counting from 0 to 15. It's selecting 0, 1, 2, 3, 4, all the way through to 15. So it's selecting 1 byte at a time out of my ROM, and the 8 bits of the ROM are coming out here into this 8-bit LED display here. So as I increase the counter, it points to a different byte of ROM, and we get it displayed on the screen. So obviously I've made it make a kind of a pattern kind of thing. And the lights on the boards here just tell you which board is currently active. So there, the top board's active. We're reading the bytes out of that one. So the top board here has got a 1 in the top position, which you can't see. There we go. The top board here has got a 1 in the top position. And then the next byte, I've selected bit 2. So if we go to there, we're on 2. And we work our way through. And then we come onto the second board. And there we go. So we're currently looking at this byte here. So if I change some of the bits on it, you can see that they come on there. And we'll move on to the next byte. You change a bit on that one. Oh, I'm wrecking my pattern now. We work our way through the sequence. So we're back to the top board. And then on the second board, I've messed it up a little bit with some extra bits that I've added. Now, why do I want to do all this? Well, because I want my homemade CPU to be able to run a program. And I was thinking, where can I put the program? I want to have a program that I can change really easily. I'm not imagining it'll be an incredibly long program. And rather than having to go to the computer every time, like connect up to a PC and change a program in a ROM, every time I wanted to change something, I thought if I just have 16 bytes of ROM here, I should be able to just change the program. So let's say the first instruction, let's have a look at this a little bit more closely. So let's say the first instruction, we wanted to do a 0 instruction, so we might have an opcode 0. That'd probably be a NOP, wouldn't it? I can't even get that to go. Got him. And then we might want to do an instruction 128. And then the next instruction in our program might be an instruction 2, and the next one might be an instruction 15. So I can obviously design the instructions however I want because I'm making the CPU. But if I'm following the 6502, then I should really copy the opcode numbers out of the 6502 opcode manual. So what I'm going to do next is link this this 16-byte MAN-PROM up to my 6502. I'm going to put various different instruction codes into the 16 bytes, and then I'm going to see if I can actually get a program running. So I want to get the program counter and the program that I've got in my ROM linked up to the controller board so that the controller board can do the fetch, decode and execute cycle, which is going to involve fetching a byte of memory, in fact the first byte of the program from memory, into the instruction register, which is this register here. So if, for example, we fetch, well, you can see we've got a value of 2 in here. So that's what would happen if we fetched a 2 from memory. If the first instruction in the program was a 2, it would appear here in the instruction register. And what I've done is, because I haven't linked this up to the memory yet, I've just taken the 8 input wires, I've put them into this plug block here that you can hardly see at the back, and I've wired them up so that all of them are 0, all of them are low, except for one of them, which gives us a 2. So I'm fetching a 2 effectively. The value that we fetch here, the instruction we fetch, is then decoded into, well, it's going to be 3 sets of 8, so 24 different lines, and each set of 8 is decoded by one of 3 EPROMs, which are going to go here. So I've imaginatively labeled them EPROM A, EPROM B, and EPROM C. EPROM A is going to decode the publish and store commands to move data around between the registers. EPROM B is going to control the ALU, and EPROM C is going to control some other miscellaneous state that I haven't thought about yet. But what I want to do is connect up the scope like this and see what the waveforms look like that are coming out of the publish and store commands, or the publish and store lines, when we go through an instruction. So if I can line things up so that you can see the 16, well, the counter that counts the 16 microcode instructions here. I've got a clock, well, it's just about in shot, and that clocks our way through the 16 microcode instructions for a particular, I shouldn't call them instructions, I should say the 16 microcode stages for each instruction. So we're going to go, so we're on instruction number 2, so opcode 2 effectively, microcode stage 0, and we're going to work our way through up to microcode stage 15, and everything seems to be going quite well. So when we're on stage 0, we're fetching a 2 because I've contrived a kind of 2 to come in, and we're decoding that into here, and the 4 bits of here are the publish and the other 4 bits are the store. And I think I've got this the wrong way around, because I've programmed into EPROM A that instruction 2, the first thing it should do is publish from register 0 and store in register 1. So that should be the other way around. It should go 0, 0, 0, 0, and then it should go 0, 0, 0, 1 in that side. So I think I've messed up my programming of my EPROM and got things upside down, but we'll just go with that for now. So microcode stage 0 for opcode 2 is publish from location 0, publish from register 0 and store in register 1. And if we clock on to the next stage, we are publishing from register 1 and storing in register 2. And then if we clock on to the next stage, it's all ones, and I'm just using that as a sort of don't do anything. So for each instruction, instruction number 2, opcode 2, we can do 16 stages, most of which are set to not do anything, but the first 2 stages are set to publish 0 and store 1, publish 1 and store 2. So first let's just look at the clock pulse. So if we trigger on, I've got channel 1, the yellow channel, I'll trigger on some clock pulses. So that's the clock pulse. The clock goes high, clock goes low, clock goes high, clock goes low, and I've got that set to 2.5 volts, 2 volts per division. So it's a 5 volt square wave, or roughly square. I mean, I'm generating it with my finger, so it's never going to be massively square. And if I now hook up the blue trace to be publish, let me see if, so we're on microcode stage 15. We're about to go to microcode stage 0. Microcode stage 0 is where something interesting happens. It's a publish 1 because I got them the wrong way around. I meant it to be a publish 0, but it's a publish 1. So let's see if we can capture a little bit of that. There we go, perfect. So what we see here is the clock is going up and down as you would expect a clock to do. The publish, the blue line is publish. This is publish one of the registers. Normally it's a high, and for the whole of the clock pulse it drops low. It stays low for the whole of the clock, one clock cycle, and then goes back to being high again. So that means that data from whichever register this is, so this is actually register 1, data from register 1 will be published onto the data bus for the whole of one clock cycle. So we've looked at publish, now let's look at store. Let me see then if I can capture a I'll have to clock myself around to stage 15. Now we're on the last microcode stage of the previous instruction. We're about to go on to the next instruction, and in this instruction we are going to publish from 1 and store in 0 because I've got my ROM backwards. Let me see if I can capture one of those. Okay, so I managed to capture that then. So here's a clock, 2 clock pulses basically. Here's 1 clock pulse. I'm saying a clock cycle is from where we go high to where we go high again. So this section here is 1 clock cycle, and store is a positive going pulse that only takes place for the second half of the clock cycle. So the publish drops low for the whole of 1 clock cycle, and the store goes high for half the clock cycle. So we publish data onto the data bus from one of the registers for the whole of the clock cycle, and this high going edge here is where the data is then stored into the other register. So in 1 clock cycle we can transfer something from register 1 to register 2 by publishing 1 and storing 2. So what I need to do next then is connect up the memory and the program counter that I've already made to the controller, so that the controller can load, well basically fetch something from memory, location 0 let's say, then increase the program counter, and then it will fetch from location 1, then increase the program counter, and carry on working its way through the memory, fetching as it goes.